So let's start starting with the first one. Okay, so state the meaning of what a transition metal is. It's something that forms stable ions. It's a D block element that forms stable ions with incomplete D subshells. So D block element and forms stable ions with incomplete D subshells. Okay, that's what a transition metal is. Complete the diagram to show the arrangement of d orbitals. So he's talking about the splitting in octahedral and tetrahedral complex. I'll just give you a brief recap of what that means. Okay, let me open the notes. This one. So what happens here is so what happens here is this is your transition metals. And when a complex is formed, the complexes are colored. They're often colored. And the reason why they're colored is because of this, that you had a D subshell and the D subshell had electron densities between the axes, and some of them had electron densities on the axis. So when you form a complex, it becomes, because of the lone pairs which are right next to the atom, it becomes harder to keep electrons in orbitals that are very close to the place where ligands exist. So the D subshell is going to split up. In an octahedral complex, most ligands, they approach the atom on the axis. So any orbital that lies on the axis, it's going to become harder to keep electrons over there. So dx square minus y square and dz square, that becomes harder to keep electrons, whereas it becomes easier to keep electrons between the axes. So your D subshell looks something like this. I mean, this is your typical D subshell. So some electron densities lie on the axis, some electron densities lie between the axis. So we're going to answer this one. Okay, what happens in an octahedral complex? It becomes harder to keep electrons on the axis. So 3dx square minus y square and 3dz square, they because of greater repulsion, it's harder to keep. So they're at a higher energy level, whereas the other ones, the ones that lie between the axis, 3dxy, 3dxz, and 3dyz, they would be at a lower energy level, and it would be, so you'll just draw 2 boxes over here and 3 boxes over here. And what happens in a tetrahedral complex? In a tetrahedral complex, it's the opposite story, which is in a tetrahedral complex, the ligands are not approaching on the axis. So it becomes harder to keep electrons between the axes. So over here, it would be the opposite scenario, where between the axes, in the D subshell, it would be harder to keep electrons and easier to keep electrons. And it would be easier to keep electrons on the axis. And there's going to be an energy gap that would be created in both cases. And that leads to colors of complexes as well. So sketch the 2 types of d orbitals, one d orbital from a lower energy level in an octahedral complex, and one in the higher energy level. So lower would be 3dxy. So the electron density would be between the x and y axis. So that is how it's going to look like, 3dxy. And one at a higher energy level, that would be on the axis. So it would be 3dx square minus y square, where the electron density would be residing right on the axis. So you've sketched the 2 types of orbitals, one over here and one over here. The next part is, this is about EDDA, EDDS and EDTA. These are polydentate ligands. What's a polydentate ligand? It's a ligand that is capable of forming many dative bonds. There would be examples of polydentate ligands over here. This is an example of EDTA. The metal line is right in the middle, and the molecule is a complex. It's a big complex molecule, and the lone pairs are approaching from all sides to form dative bonds or getting attracted to this metal line over here. So on the diagram, circle each atom that forms a bond with Fe3 plus, ion in Fe. So circle each atom that forms a bond with Fe3 plus, EDDS. Now, EDDS has a charge of 4 minus. So it's got a charge of 4 minus. Fe has a charge of 3 plus, which is why the overall charge on this thing is -1. So who's forming the bonds? And did he say that it's forming? He's saying that they form octahedral complexes. So this molecule would form 6 dative bonds if it's an octahedral complex. So that means a lone pair over here, a lone pair on this oxygen over here, a lone pair not on the carbon but on the oxygen, that will be datively bonding. This one, there's an N lone pair that would also be bonding. So there would be 6 lone pairs that will be attracted, and something similar to this would happen. That the lone pairs from all sides will surround it. Okay? Is this part clear? Sam, Munir, is this clear?
Sir, why 6?
He's already said it's an octahedral complex. What is an octahedral complex?
It forms 6.
Yeah, I mean, this is an octahedral complex that forms 6 dative bonds. I mean, this is a tetrahedral complex. So whatever happens, it's going to form 6 dative bonds like this from all sides. I mean, similar to this, like you put Fe3 plus over here, so all these lone pairs from all sides are going to come in and they're going to surround it and they're going to form 6 dative bonds. That's when you have an octahedral complex. Okay. The other part is the one is red and the other one is yellow. Explain why the 2 complexes have different colors. So what you're going to do is the 2 complexes have I mean, they are different, I think. It's got a bigger carbon chain. That's probably the only difference. Between over here, there's 2 carbons. Over here, even the carbons are kind of similar. I mean, the structure is different. Sorry, the position of the N is different. So the molecules are different. So why do complexes, the question is, why do complexes have different colors? So different, because the ligands are different. So when you have different ligands, and their lone pairs will exert a different amount of repulsion. A different amount of repulsion on the D subshell. So a different energy gap is going to be created. I mean, this is what's going to happen, that okay, if you have colors pe. So this is what's going to happen, that if you have different lone pairs or different ligands, the repulsion that's going to be exerted on the D subshell inside the atom, that is going to be different. So the splitting would be different. The energy gap that would be created would be different. Maybe it becomes really hard to keep electrons in the green orbital over here. So the energy gap would be much bigger in that case. So we don't know, but the energy gap would be different. So different energy gap exists between your higher energy and lower energy D subshell. And if there's a different amount of energy gap, so different, since E is proportional to frequency, or delta is proportional to frequency, a different frequency is going to be absorbed from the visible spectrum. I'm just going to compare this one with the MS as well. It's just a 2-mark question. So what exactly were they looking for? Usually it's a 3-mark question. So we'll just quickly confirm. So I think it's just that, I mean, they've just said that the delta E has to be different and a different frequency is absorbed. I mean, they weren't looking for the complete explanation, just looking for these 2 points. Now, coming back to this, I mean, this was a total explanation. If they had given you 4 marks or 3 marks for this, you would write all of this. Now, state the type of reaction that occurs over here. What type of reaction is happening over here? This EDDS comes in and replaces the water molecules. So it's a ligand exchange reaction. So that is what is happening, ligand exchange. Moving on, you have to write the K stability for FeEDDS. So the K stability constant for this one would be, it's just basically Kc for this. So K stability for EDDS is going to be product concentration. Since it's aqueous, you're not going to write water. So it's going to be Fe EDDS, its concentration divided by the reactant concentrations. So the reactant in our case are going to be Fe with 6 water molecules. And it's 3 plus its concentration into EDDS 4 minus 1 concentration. Everything is 1, 1. So all the exponents would be 1. Just don't write water in the expression. That's your K stability value. And the table shows the values for the stability constant of both complexes. Remember, a higher K stability value means more ligand exchange would happen. So more product would be formed. I mean, the lower one has a. So more product or more of the complex is going to be formed. Explain your answer. Predict which of the complexes is more stable. It's this one. Why? Because it's got a higher value. That's it. 1 mark, and that's it. So remember, the K stability value is only going to be higher if the numerator is bigger. If the numerator is bigger, that means more product is being formed. This is basically product over reactant concentration. As I explain your answer with respect to K stability, so we did that. When an excess of ADTF4 is added to this thing, the following equilibrium, so there's another ligand exchange happening. The equilibrium constant Kc for this equilibrium, using the K stab values given in table C5. So he's saying link the 2 things up. Figure out or calculate Kc. What is Kc in this case? Kc in this case is the product concentration, which is this, it's Fe, EDTA minus its concentration into EDDS 4 minus 1 concentration, and this is what you're looking for. You're trying to calculate this divided by the reactant concentration, which is Fe EDDS minus concentration and EDTA 4 minus concentration. So we're looking for this value, and he says use the values that are given above. So I'm just going to use these 2 expressions, which I already wrote. That for EDDS it was this one. For EDTA it's going to be exactly the same one. It's just going to be EDDS getting replaced by EDTA. This one getting replaced by this one. So both of them are going to have exactly the same expressions. So I'm just going to copy. It's just time consuming. I'm just going to copy those 2. So I'm just going to copy K stability for EDDS. So that is Fe with EDDS, and that's minus 1. Just copying this expression over here. divided by Fe with 6 H2Os and EDDS 4 minus. So Fe with 6 H2Os and it's 3 plus and EDDS 4 minus, I guess. And the other one, that's the first case stability. For EDTA, it's exactly the same. That would be EDTA minus 1, its concentration divided by Fe with 6 water molecules. It's got a charge of 3 plus and EDTA 4 minus. Now I need this expression over here. So what I'm going to do is I would have to multiply this thing. The two things need to be multiplied, but this would be 1 over. I mean, I have to take the reciprocal of this because FE-EDDS must come in the new denominator. FE-EDTA must come in the numerator. And if I do that, EDDS 4 minus would automatically come in the numerator. EDTA 4 minus would remain in the denominator. And two things are going to get cancelled out, and that's Fe with 6 H2Os and Fe with 6 H2Os if I multiply the two things, okay? And I'm going to get this expression. So basically the link is it's this value multiplied by the reciprocal of this value. So it's 1.26 times 10 power 25, which is going to be multiplied. I mean, this thing is going to have this value. It's going to be 1.26 into 10 power 25 multiplied by 1 over 3.98 into 10 power 20. So the Kc for this reaction can be obtained by using the K stability expressions of this one and this one. Okay, is this question clear?
Say.
Yes, sir.
Say no, I didn't understand it a little bit. Sorry.
Okay, I'll start with this one. Like you do know what K stability is, right? So when you
I do.
Okay, when you have an aqueous complex, you add a certain ligand and a ligand exchange happens, right? So so its K stability is basically the Kc for that. It's when you write the K stability of FE-EDDS, it's basically you had aqueous ions surrounded by water, and this ligand came, and so it's product concentration divided by reactant concentration. That's the expression, right?
Yes, sir.
And the one with EDTA is going to be exactly the same as well, right? Is that clear as well? Because it's going to be the same equation, except for instead of EDDS, it's going to be. Yeah, so is that clear that the other one is also going to have exactly the same expression, right?
Oh, yeah.
So you do have the complexes. I mean, you do have the value for K stability for both of them, right?
Yes,
so one of them was K stability 1, which was this expression. I mean, the only difference between the two is the other one had EDTA, this one has EDDS, right? Is that clear as well?
Yes, sir.
Now, he's looking for the Kc for this expression, which is this one. So I wrote down the expression for this. It's product concentration divided by reactant concentration, product over reactants, right? So he's asking for the value of this one, this Kc, right? So is that clear as well?
Yeah, I'm with you now.
Now, he said that use K stability values given and calculate this Kc, the one that's over here. So I figured out that the first K stability had this expression, the second K stability had this expression. Can I use the two expressions to make this expression?
Okay.
And I figured out that if I multiply this, this expression with the reciprocal of this, I'm going to get this expression. I mean, you can do the math. I just don't want to write the whole thing. This would be the if I multiply this by the reciprocal of this, right? So it's going to be FE-EDTA divided by the FE-EDDS. So it's FE-EDTA divided by FE-EDDS. And the denominator is going to be EDTA 4 minus. And the denominator over here, if I take the reciprocal, it would become the numerator. So it's going to be the exact same expression. And it's going to give me this. So I figured out that the Kc over here is basically this being multiplied by the reciprocal of this, and that's exactly what we did. This
Okay.
being multiplied by the reciprocal of the other one. So is
Okay.
that clear to everyone?
Yes,
It's
sir.
clear. I understand.
Achha, so now moving to the next part, we've got so this is about, I think, cisplatin and transplatin, or something like that. Describe the action of cisplatin as an anti-cancer drug. So they started talking about cisplatin, but they didn't actually draw cisplatin. So what's the action of cisplatin? What it does is, cisplatin is this molecule. It's a platinum ion. It's got two NH3s. It's a square planar molecule, and there is Cl. So platinum is actually 2+. You've got Cl-1 with its lone pairs getting attracted to it, and you've got N lone pairs getting attracted to it. Now, what happens is that what cisplatin does is that it binds with it goes into the DNA and binds with the nitrogen bases in DNA, which makes it impossible for it to replicate. So the DNA is not able to replicate. I mean, DNA has, like, if you're a biology student, it's got these bases. It's a ladder-like structure, and it's got these nitrogen bases that are coming out of it. Now, what cancer is that your DNA structure, which has all the information about protein synthesis, it gets damaged. So the nitrogen bases have a certain order, and that order gets disturbed. So any cell that is produced using that DNA is going to be either benign or it's going to be a useless cell, because it's not going to make the right type of proteins. So the order of the bases is very, very important. So once the cell degenerates and it becomes useless, it should stop replicating, because if it replicates, it's going to create tumors in the human body, and it's going to spread and it's going to multiply uncontrollably. So what you do is the cisplatin would come in. The lone pairs on N over here there's going to be a ligand exchange type reaction, and the cisplatin would bind with the DNA. So it's just a 2-mark question. You just have to write a simple statement. I'll just check the marking scheme for that. It's just going to be a very, very simple basic statement that the cisplatin binds with the DNA nitrogen bases. I mean, the 4 bases, adenine, thymine, cytosine, and guanine, ATCG. And it prevents the replication of the DNA. That's about it. This is I mean, you don't have to write a lot of detail about that. I said, moving to the next question. Just remember, cisplatin is an anti-cancer drug. Now, moving to the next question, we've got suggest the geometry of the platinum center of the carboplatin complex. It's square planar. You have to remember this. It's square planar. Cisplatin is square planar, and it's capable of forming geometric isomers as well. Suggest why carboplatin does not show cis-trans isomerism. So what is carboplatin? It's I said this one. A reason it can't show cis and trans is that you can't put NH3 over here because the molecule is a bidentate ligand, and you can't break a bidentate ligand. Like isomerism is, I mean, what is geometric cis-trans isomerism? That NH3s are pointing or right next to each other, or NH3s could be opposite to each other. Cisplatin had geometric isomerism where the platinum, the NH3s could be at extreme opposite ends, and the Cls could be on the other ends. So that was a trans version of cisplatin. But this one cannot, because the bidentate ligand has to be broken. Like, if I have an NH3 over here, the other NH3 cannot be over here, because the 2 bidentate ligand lone pairs have to be next to each other. So how do you describe that? It's just 1 mark. And this is what I mean, I'm just going to use the words over here in the marking scheme, which is that the distance between the two coordinating is too small to bond trans, or you can say that it's a bidentate ligand and can only bond on or you can say that it can only bond on adjacent because it's bidentate. The geometry is limited. They can only bond on adjacent or 90 degrees to each other. They can only bond 90 degrees to each other. This oxygen cannot go and bond from the other side, because then you would have to break this. Then this one you've got is a natural complex containing CH3, this one and this one and this one. Reduce the oxidation state of platinum in Tetrahedral. So he's saying Tetrahedral is a neutral complex. It's got platinum in it, and it contains all of these ligands. So it's got CH3, CO2 minus one ligand. It's got so that's one. It's got C6H11 and NH2 as a ligand. It's got a Cl minus one ligand, and it's got an NH3 ligand as well. So and it's a neutral complex. So it's neutral. So what is the overall charge? The overall charge should be 0. Yeah. This is neutral. This is neutral. This is -1, So platinum has to be +2. DK, is that clear as well? Clear, yes or no?
Come again, sir, please.
Need this one. Is this clear? Not clear? No. I mean, it's just that you had to figure out what the charge on platinum. He said that
okay.
He talked about platinum.
Okay, yes, that's true.
So it had all these complexes, and the overall charge was neutral at 0. So it can only be 0 if this is +2. Now moving to the next one, reduce the structure of L. What is L? So you've got this thing, and it's turning into that other thing, which is M. So how do you do that? It's I mean, you're turning it into, so it's probably making it into a carboxylic acid. So how do you turn it into a carboxylic acid? That is oxidation. If you oxidize an arene, the carbon chains are automatically turned into carboxylic acids. So they're going to turn into acetyl bond O and OH, and this side would also turn into acetyl bond O and OH. And acyl chlorides can be formed from carboxylic acid. So we did figure out the structure of L. Reagents and conditions. This is oxidation. That's KMnO4, acidified, and reflux. Now this other one. So this other one is how do you get rid of the OH and replace it with Cl? That's PCl3 plus heat, or SOCl3 plus SOCl2 plus heat. So that's how you do it. So then the next one is write an equation for step number 2. So you have to write an equation for step number 2. So I have a PCl3, and over here I have what do I have? I have C6, and I've got 4 H's, right? Because 2 of the carbons have been substituted. There's another COCl and another COCl on the other side as well. So I'll just put 2 over here. And they're reacting. So this C6H4 would become, sorry, it was carboxylic acid initially. So it had 2 carboxylic acid groups. And now it will have acyl chloride, 2 of them. And what else is produced? HCl is produced, and H3PO3 is also produced. Very rarely that they actually ask you for the complete equation, which in this case, they are asking for the complete equation. So it's going to be this one. And they've actually, in a number of instances, they've actually asked for this equation with PCl3 or SOCl2. You can have a look at the marking scheme, which is this one, that you can use PCl3, you can use SOCl2, you can use PCl5. Pretty hard to actually remember the equation. In this case, what I got wrong was I shouldn't have written HCl over here. The HCl is not there. It's just H3PO3. So very rarely do they ask for the whole equation. It's just a 1 mark equation anyways. But in this case, they have actually, just hold on 1 second. In this case, they have actually asked for the equation. Now, the other part is a student investigates a possible synthesis of FEM directly from benzene using COCl2 in the presence. I mean, what is COCl? In the presence of an AlCl3 catalyst. So benzene initially reacts with COCl2 as shown. Reaction 2 is the electrophilic substitution of Cl, C plus, or whatever for H plus 1 in benzene. Suggest a mechanism for reaction number 2. So you know that if you remember benzene's reactions, there was electrophilic substitution, and what would happen in electrophilic substitution is that an electrophile would approach it. So benzene's electron cloud would be attracted by, so there's this double bond O and Cl, and it's a positive charge. I mean, this one over here. So there is an electrophile that is going to approach it, attack it. It's going to try and steal the electrons from the benzene electron cloud. So the next step would be that the electron cloud would become partial, and this carbon will come and bond with that particular carbon. It's going to steal electrons. The benzene electron cloud would become partial. There's going to be an H over here. And in the next step, the H would leave. The H would give away its electrons, and it would eventually leave. So it suggests a mechanism for reaction number 2. That's what's going to happen. It's just like an NO2 plus 1. Most electrophilic substitution reactions you had, and I'll also open the. I'll show you what's happening. And if you look at your notes, so remember this. 1 second. So remember this, that benzene had electrophilic substitution, which was this one. That a positive electrophile would come and approach it, and that positive electrophile would steal one of the electrons from the pi electron cloud and bond with it. And the next step, a carbocation would be, the benzonium ion would be formed. It will have a positive charge, and the H would then have to give its electrons back and leave. And in that step, the Br will be substituted by, so the H over here will get substituted by Br. And you had a similar reaction with NO2 plus 1 as well. The NO2 plus 1 would come in, same thing, etc. Everything was same. So that was another mechanism. So this one is exactly the same. Now the next one is, you've got Framatic Acid. Identify the products of the reaction between this and hot concentrated. Hot concentrated KMnO4, the double bond will completely break. It will break, and the rule is that if the double bonded carbon atom has 1 carbon chain, it turns into a carboxylic acid. So there was a carboxylic acid on one side already. The other carbon will also turn into a carboxylic acid. So if the carbon that was making the double bond had only 1 carbon atom, it will turn into a carboxylic acid. The other side would be exactly the same. So this is the product that's going to be formed. Now, fumaric acid can form addition and condensation. Draw the repeat unit of the addition polymer. So you've got a double bond in between. There's carboxylic acid on one side, and there's a carboxylic acid on the other side. And H and H. How do you draw the unit of an addition polymer? That it's going to link up. The double bond in the middle would go away, and you write N over here. That's going to be your repeat unit. And draw the structure of the unit of polyester which is formed with ethane 1,2-diol. So a repeat unit. So again, you had a double bond. It had carboxylic acid on one side and carboxylic acid on the other side. And you had H and H. And the other one is a diol. It's CH2OH. So it's got CH2OH on both sides. So what happens is an ester would be formed. These two would get removed from the middle. And they would link up in the middle. That's a condensation polymer. And the ends, same thing would happen at the ends as well. The OH is going to get removed and the H over here is also going to get, it's also going to get removed. So there's going to be a continuation bonds over here and continuation bonds at the other end. And that thing is going to get, it's going to be repeated over and over again. So that is what your condensation polymers is. And why polyesters normally degrade more than alkenes? Because they're polar. Polyesters have a polar, it's a highly polar ester linkage. So it attracts water. I mean, this carbon over here is positively charged. So if a water molecule is roaming around, that water molecule with its lone pairs is going to be attracted to this carbon atom. So it's going to, I mean, this, and the repulsion from the lone pair will sort of knock this bond out. Bond is going to break. So polar ester linkage attracts water, which is why it easily hydrolyzes. Which is why amides and esters both are biodegradable, because they very, very easily hydrolyze. And fumaric acid reacts with cold dilute acidified KMNO4 to form the compound P, and it exists. Only 3 isomers of P exist. One of the stereoisomers is shown. Complete the 3-dimensional diagram in the boxes below to draw the other 2. So the only thing you have to do now is, he's saying that this is chiral and this is chiral, both are chiral, right? So the other ones are what are stereoisomers? The other ones are mirror images, right? So you're going to have 2 of them. In one of them, one side will be mirrored. I mean, the other version. In the other version, the other side would be mirrored. So you keep this side the same. You have an OH in the same position. But this side over here is now going to be mirrored. So if you mirror this side, it's going to be COH, and it's going to be COH. The H would be this side, and the OH would be over here. So I've mirrored this side. Now in the other one, I'm going to mirror the other side, which is going to be, let's keep this side over here, the H over here. The OH is at the same spot, but I'm going to mirror the other side. So if I want to mirror the other side, what will happen is you've got a COH. The H will be over here. Remember, mirroring can happen in many ways. Like over here, what I'm trying to do is that H is right now pointing into the board. If I mirror it, it now starts pointing out of the board. So the wedge-shaped bond is now H. The OH is pointing out of the board. If I mirror it, it starts pointing into the board. So those are the 2 sides. In this case, this is mirrored. And the other one, the other side is mirrored. Is that clear?
Do you mind if you come again, please? Sorry.
Like if you know that, you know what chiral, how to draw chiral molecules, like if you want to show stereoisomers, right?
Yes, sir.
So what you do is W, X, Y, and Z. So how do you mirror things, right?
Mm-hmm.
The way you mirror things is, I mean, there are many ways to mirror this. It's just you're going to invert it, right? If I want to mirror this thing, I can do it left to right, right?
Yes, sir.
If I do left to right, it's going to look like this. It's the dotted would come over here, the wedge-shaped bond would be over here, and this one would be over here. So I'll have W, Z would be on this side, X would be on this side, and Y would be over here, right? Is that clear?
Yeah. Yes, sir.
So, but that's one way of mirroring things.
Mm-hmm.
What if I mirror it front to back? Like, I mean, I'm mirroring this if this is the center I'm choosing, right?
Yes, sir.
So, but I can mirror it at any point. Like what I can also do is I can mirror it upside down. Like if the other one, let's say I put a mirror over here. So how would this molecule look on the other side, right? How would it look like? It's going to look something like this. If I mirror it, it's going to look. Is that clear as well?
Yes, sir.
That W would be over here, Z would be over here, and X would be over here, and this would be, I think, Y. So,
okay, understand.
So the point I'm trying to make is there are many ways of mirroring this. There's another way of mirroring this. What if I do front to back, like the screen, your computer screen, that's your mirror. So, and think of the molecule as being behind that mirror. What if you want to bring it towards yourself? Then the molecule will be mirrored front to back. What will happen is this Y over here is right now coming out of the page, right? This one. So if I mirror it, if I put the mirror, like if the screen is the mirror, then in the other mirrored version, the Y would be inside the board, right? Is that clear?
Yes, sir.
And the Z right now is going into the board. And if the screen is the mirror, on the other side, it's going to be coming out of the board, right? So the point I'm trying to make is, like, you're used to drawing one mirrored version, right?
Yes, sir.
So the mirrored molecule could be the other non-superimposable mirrored version. If you keep the mirror over here, it's going to be laterally inverted, left to right, right? If you put the mirror on top, it's the exact same thing. It's exactly the same thing, except that it's now just mirrored top to bottom, right? Or in the third case, which is this one, if you think of the screen as the mirror and this molecule as being behind that screen, so in the mirrored version, the bonds that are coming out of the page are going to be going into the page, and the bonds that are going into the page would be coming out of the page. And these two bonds would remain right on the screen, right? Because they were already in the same plane. So they wouldn't get mirrored. So that is what I did over here. This molecule had two chiral centers, right? So since it had two chiral centers, there could be two mirrored versions. There could be other versions of the molecule. Like either this side is mirrored or either this side is mirrored. So what I did was I drew another version of the molecule where I mirrored the left.
Okay, I'm with you now. I do understand now where you're coming from. Yeah, thank you. And
then what I did over here was I drew another version where I kept this side exactly the same, but I mirrored the other one.
Okay.
So that's about it. So let's so just make sure make sure to remember this. Like it's slightly confusing, but make sure that drawing mirrored version, you're used to drawing this one version of the mirrored version, right?
Yeah.
It depends where you keep the mirror, right?
Yeah.
Like if you're standing in front of the mirror, one version would be that you're standing right face to face with yourself in the mirror. That's one mirrored version. But maybe you're standing sideways. Then that would be, it would be the same thing. It's the same mirrored version, but it's going to look different, right?
Yes,
or the perspective would be different because you've rotated yourselves. So this is something that's important. So make sure you remember this. So let's continue next time then. We'll continue with the same paper next time. Okay, everyone.
Thank you, sir.
Thank you. Take care.
Thank you.